In the last video in this series, we have a new bakery, sorry, a real world application. So let's read it. It says a new bakery offers decorated sheet cakes for children's birthday parties, and other special occasions. The bakery wants the volume of a small cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake, and the height of the cake to be 1/3 of the width. What should the dimensions of the cake pan be? All right, so let's tackle this problem. Okay, I would actually start by drawing a picture. Okay, so this is my rectangular solid. Let's see what they're telling me about it. Okay, they are saying that the bakery wants the volume to be 351 cubic feet. So the volume is 351 inches, cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width. Okay, so we have length, we have width, and we have height, right? So they're saying length L is 4 inches longer than the width. So W plus 4. Okay. What else are they telling me? The height, 1/3 of the width. So H is 1/3 of the W. Okay. Now think about which formula will work here. Which formula ties what we have, what we need to find? Well, we have volume, right? So we have length times and height, sort of. We have expressions for those. So we're going to be working with a formula for the volume of a rectangular solid. And that formula is length times width times height. Basically, that's it. Now let's put in what we have in this formula. Well, we have volume of 351 cubic inches. I'm going to leave, oh, let's actually carry them. The length is W plus 4. Well, the width is W. And the height is 1/3 W. Okay. So I think we can do that. Now we have an equation with only one variable. So I'm going to leave out the units for now. So 351, and I'm going to multiply W into W plus 4. Or I could actually multiply it. Yeah, let's multiply it into 1/3 W. It doesn't matter at all. But we have 1/3 W cubed. And the reason we're doing this is because we can only solve it when we have a 0. See, like this is factored, right? But the fact that we have a number on the other side of the equal sign doesn't help. We can only do it when we have 0 on this side. So that's where we're going with this. So I'm gonna also distribute this term and then bring the 351 over. And this is W squared. I just noticed a typo on my part. Okay, so multiplying 1/3 W squared in, we have 1/3 W cubed, and then multiplying by 4, we have 4/3 w squared. And now I'm gonna bring the 351 over. So 0 equals 1/3 w cubed plus 4/3 w squared plus 350, well, minus 351. All right, so now I have to factor this guy. And I see that I have coefficients of 1/3, 4/3. I don't like it. I don't like working with fractions when I have to factor. So what I'm gonna do, I'm gonna actually multiply everything, both sides of the equation, by 3. I have the right to do that. And I will exercise that right because it's gonna make my life easier. Okay, so 3 times 1/3 is 1. So I have w cubed plus 4/3 times 3 is 4. So 4w squared minus, well, was 351. It's gonna go up to 1053, I think. Yeah, looks like that. So 1053. So this number became higher. So next step, this is a third degree polynomial. We can't use anything, so we need to actually fish for zeros. And Descartes' rule of signs tells me that we have one possible real zero, positive, one possible positive real zero. So since the leading coefficient is 1, when fishing again for possible zeros, so possible zeros, using the theorem, it's going to be factors of this term divided by factors of that term, which is always 1 for this trinomial. So just basically factors of this term. So yeah, we have all those zeros that we're hoping that one of them is going to be our one possible zero. Okay, so we have a long list to check. Let's hope that it's going to be one of the first ones. Okay, but we're going to check only the positive ones now. Okay, so let's use our synthetic division, and we have 1 for the cube term, 4 for the squared term, 0 for the w to the first, and negative 1053. Now we're dividing it by, well, let's do the positive 1 first. So 1, 5, 5, and 5. So this becomes negative 10,048. So obviously not it. Oops, you guys don't see it. There you go. Let's try 3. So 1, 4, 0, negative 1053, and we're dividing by positive 3. So 1, 3, 7, 21, 21, and 63. So I'm not gonna even, I don't have to figure it out. It's all I need to know that it's not 0. So moving on. But it gives me hope though, because look, these numbers are like stayed small. These are like increasing, which here this value is going to be less. I mean, absolute value is going to be less than that. So that gives me hope that maybe 9 or 13 is going to be it. Okay, 1, 4, 0, negative 1053. And let's try a 9. Okay, 1, 9, 13 times 9 is 117. So 117 times 9. And yay, it's positive 1053. So I found my 0 right here. Okay, so uh, think about the context of our problem now. We were looking for the width value, right? That would give us that volume. And we found that there is only one positive real 0, and our width should be positive and real. Okay, we found it, and we found that it is 9. So W equals 9. Now we can use that to find all the rest of our dimensions. So since W equals 9, then L equals 9 plus 4. So that's going to give us 13. And H is 1/3 of 9. So 3. So my dimensions of the cake are going to be 13, 9, and 3. That's it. That's how we apply this information. All right. So now I want you to try one by yourself. Okay, try this one. It reads, a shipping container in the shape of a rectangular solid must have a volume of 84 cubic meters. The client tells the manufacturer that because of the contents, the length of the container must be 1 meter longer than the width, and the height must be 1 meter greater than twice the width. What should the dimensions of the container be? And let me know if you have any difficulties, okay? And this is it. This concludes our section 5.5, zeros of the polynomials.